Yes, welcome student for our lecture today. So today is that MA412 and so linear algebra. And the lecture number 7, I guess. Lecture number 7. Okay, so yes. Yes. So today we will discuss a very important idea, and it's called the matrix representation of matrix representation of linear maps. Okay. Yeah. So yeah. So we'll start with linear spaces with finite dimension finite dimension, and we will relate with respect to some basis, obviously. So okay, so let me tell you that we will assume something called order basis. So what is that? So order basis is a basis with some order, with some okay, so what do you mean by ordering? So I should say that ordering on the basis vector. So maybe I will give some example. Okay. So for example, let me just give very basic example one. Suppose it is my R2 over R. Okay. So in the Cartesian coordinate system, we generally have this kind of basis 1 0 0 1, and this is called the standard order basis. This is ordered by means this is the first vectors v1 and this is the second vector in this ordering. Okay, but obviously you can change the ordering also. You can write down the first one 0 1 and this, right? That will be a different ordering, right? For example, if you choose, so as I said, if you choose say b dash by 0 1 and 1 0, so as I said they are same, but when you talk about the ordering they're different. Okay, for example, here the first vector is that 0 1 vector and second one 1 0 vectors, but here it is the opposite one, right? So when you talk about order basis, we will say that the b and b dash are different bases, not the same basis. Okay, this is called order basis, though as I said they are same. Okay, the ordering are different. So while we are throughout this discussion, we will always assume that we have an order basis of the unintentional vector space V, and then what you can do, then maybe so let me just discuss some more things. Suppose we have a V vector space V, and say B have a basis, or rather I should say the ordered basis, ordered basis of a finite dimensional vector space, finite dimensional vector space or linear space, whatever. vector space V with say dimension of V equal to say assume n. Okay, suppose this is my n. Okay, and then another question is that okay, so what does that mean? That means if for any element of V, for any V belongs to V, there exists some constants, say C1, C2, Cn, and okay, so maybe I should write down also field what the field F. The element of the field F such that what happened such that you can write down your this small v in terms of linear combination of the basis vector, right? So let me assume that my basis vector has basis vector small v1 up to vn. Then I can write down this as summation ci vi I equal to 1 to n. Okay, this you already know, right? Now this so with respect to this presentation, we will define something called the coordinate vectors. So we say the coordinate vector of V with respect to this basis, this order basis. Okay, V is so we will define this by symbol this kind of things with respect to B. This is a column matrix, so we will define this as a column matrix. And how do we define? We define by C1, C2, and then Cn. So this will be this kind of column matrix, and or we can say column vector also. Okay. So this we will call the coordinate vectors, coordinate depends on whatever of V with respect to that basis. Okay. And this is, you can obviously understand that this is the natural way of doing, for example, in R2, R3, or maybe in higher dimensions Rn. You can do this natural way, right? For example, when you write down say 1, 3 in R2 with respect to the basis B, which I just wrote 1, 0, 0, 1. Then actually this, what does that mean? That means this is actually you are writing this in terms of the standard order basis 3 times 0, 1, right? And so the coordinate. So this vector actually so the coordinate vectors of these with respect to this basis will be, we write down this 1, 3. So now onwards it's better to write down by this symbol 1, 3 as vectors. Okay, then it will be the symbol will be same symbol. But if you change the basis, for example, if you change the basis, by 1, 0 and 0, 3. This is a new basis, for example, B1. Then you see that with respect to this basis, your vector will be 1 times 1, 0 and 3 times 1 times 1 times 0, 3. Okay, so with respect to this basis, what is the coordinate vectors of this with respect to this B1? So this will be, I think, 1, 1. Okay, so that's on the same point you can represent differently with respect to different bases. Okay, and those are called coordinate vectors with respect to that basis only. So now you recall that in our last lecture we proved that given a basis, the given vector space is V and W, okay, with maybe dimension of and maybe a linear map, say, so let me write down this T from B to W, and you also know that so you have a basis B, okay. So what should I write down? So maybe B1, yeah. So B is having same dimension, V is having dimension n, so B has n many vectors, and W has a dimension m. So W, so maybe what should I write down? So it's better to write down BV and BW, maybe these symbols. I mean, you can write down B1, B2, whatever, doesn't matter. So let me just use the symbols. Small w1, small w2, and small wm. Okay. So we should, what does that mean? I mean, dimension of v equal to say n, and dimension of w equal to m. Then always you can have a unique linear maps which sends this vector to this vector, right? That we already proved in last lecture. Okay. And what will be the map? That you define the images of VIs. So you choose elements WI this, and you define the images by WIs, right? Okay, so now yeah, no, so for there, if there are n vector, then you can do it, but for here also what you can do, you can take the images and you can write down in terms of these vectors. So like you choose T of V1, the T of V1 is element of W1, so you can write down this in terms of some linear combination of WIs, right? So how you can write down? You can write down, say, A11 W1, okay, plus, and then maybe, okay, so maybe A21. So let me use these symbols. I'll tell you why I'm using these symbols. Okay, so and A1 W1. Okay, so 1 2 3 4, yeah, so many vectors are there, and so what does that mean? That means so you can say that the coordinate vectors of TV1 with respect to W1 is the column vectors, this right, A1, A11, A21, A31, like that. Okay, so similarly, in general, you can write down uh, in any vector, say A, Vj, in terms of summation A, Ij, omega I equal to 1 to m, and many vectors are there, and that is you can define for all j equal to 1 to up to n, right? So in general, you can write down these. Okay, for each vector of basis of v, you take the image and then write down those in terms of linear combination of the vectors of w, and then you see that so this coordinate vectors with a column vector, if you put the column vector together, you will have a matrix. So you can write down the matrix here. So maybe define definition. So the matrix representation of the presentation of a linear T from say V to W with respect to the basis that dV and dW. So this is basically respectively. Okay. So that is defined by what? So we define this matrix representation by this symbol T of VV to VW, and that will be the matrix A whose Aij elements will be Aij. So you write down this A11, A21, A31. This is the first column vectors of the matrix, and then Aij. So for particular J, A1J, 2J, 3J, and that will be the jth column vectors. Okay, and then you can write down that is the matrix representation. So this is our definition. This we call the matrix representation of that linear map. Okay, so we will say that this for final vector space, these linear maps are nothing but a matrix by this symbol with respect to some basis. Okay, maybe we will give some example, then we will have some things understanding. Okay, so maybe example 1. So recall the linear maps we define, say R2 to R2 by remember x1 x2 by x1 plus x2 and x1 minus x2. And here I am assuming both are standard error basis. Okay, so one more thing. So when V equal to W and both are same, if you choose both matrix, both bases are same, you can choose different also, but if you choose both are same, in that case we will only write down TV is the matrix representation. Okay, instead of TV BV we write down T BV only. Okay, this is symbol for matrix representation. Symbol for matrix representation. Okay. So this is our symbol. Okay. So maybe here I am assuming that both same vector space with the same basis. And what is the basis? Standard basis 1 0 0 1. Obviously you can change and then the answer will be different. With this standard basis, what happened? So how do you calculate? So you first take that element and find out what is the image of 1 0 vector with respect to T, and that image will be what? So this will be 1 plus 0 and 1 minus 0, so it's nothing but 1 1, right? And how do I do 1 1 in terms of that? So you write down 1 1 0 plus 1 into 0 1, right? So the first column vector you got, that is 1 1. Similarly, for 0 1, what do you have? So you have 1 and then it will have minus 1, right? Which is nothing but you write down this 1 times 1 0 plus minus 1 times 0 1. So second column vector is this, and hence the matrix representation of this with respect to this basis B, what will be that? That will be 1 1 1 minus 1. This is the matrix representation. Okay, now if you change the basis, this standard error basis by another basis, you will have a different matrix. Okay, and there are relations how you can relate these two matrices that we will discuss later. It's called change of basis matrix. Okay. So this is one example. You can have many more example of this. You can have many examples. Just maybe you can consider the derivative map from this polynomial space of polynomial degree at most 3 over semi real numbers to degree. Okay, so degree at most 2. Okay, so I'm defining this polynomial by the derivative. Okay, derivative of the polynomial. This is completely is a linear map. This is not the problem. But then the question is that then how do you how to find out? So here, what we do, you will have maybe the basis. We will write down B1, which is the basis for P2 or 3, and that will be I'm taking the standard error basis. And B2 for P2R, again this is the standard error basis. Okay, now with respect to these order basis, what will be the matrix, how they look like? So again, what you have to do, you have to find out that images of this basis vector. Okay, so what will be T1? So this will be 0, right? In derivative, and that is nothing but 0 times 1 plus 0 times x plus 0 times x square, right? Similarly, tx, image of tx will be what? So this is will be equal to 1, and that is nothing but 1 times 1 plus 0 times x plus 0 times x square, right? Similarly, you have x square, whose image will be 2x, that is 0 times 1 plus 2 times x plus 0 times x square, and finally t of x cube will be nothing but 3 x square, and this will be 0 times 1 plus 0 times x plus 3 times x square, right? And hence, what is the answer? The answer matrix will be so the first vector will be 0 0 0 0 0 0. Second vector is 1 0 0. So 1. So second column 0 0. Third column is 0 2 0 0 2 0. And the last column is 0 0 3. So 0 0 3. So this is the matrix. How many rows are there? 1 2 3. How many columns are there? 1 2 3 4. So 4 3 per 4 rows, right? And that is obvious because the dimension of this is also not that, I should say here. So if dimension of this is n, dimension of this is m, so this is will be m cross n matrix. So in that case, A will be a m cross n matrix. Okay. That depends on the dimension. So if both have the same dimension, then it will be the n cross n matrix. Okay, the square matrix. In general, even may not be same, right? So it may not be square matrix always. For example, this dimension is 3, here dimension is 3, here dimension is 4, so this will be 3 cos 4 matrix. See, this 3 cos 4. Okay, so this is a nice observation to check that what will be the jth column of this the matrix T. Okay, so, or rather A. So Z column is nothing but the coordinate vectors of T Vj, right? So this is obvious. You can check that the jth column. So the way we define. So maybe I can write down here the jth column. Jth column of this matrix A is nothing but we write down the vector T V J, so the image of Vj with respect to T, and then find out the coordinate vectors of this with respect to the basis BW. Okay, and that is actually the jth column. So this is the ninth observation. You can do it. Okay, so now let us do some more interesting mathematics on this. So what happens if we collect like these linear maps of two vector spaces? For example, suppose if you have two linear maps, say T1 and T2, and that is from say V to W, yeah, two vector spaces. Okay, and if you add them, then what happens? Then this is linear. Both are linear. Then if you add T1 plus T2, so add means what? Add means you just this kind of individual addition. Okay, so this is the definition. Then what happened? Then T1 T2 is again a linear or not? Okay, so what does that mean? That means if you have two linear maps, whether the addition will be whether they will form say satisfy the vector spaces or not. How to prove? Like if we add so for first of all, if you add two linear maps T1 T2, they will be again linear, right? Because they satisfy that condition T1 plus T2. So linear means what? So you choose some CV plus U, and then this will be nothing but by definition this is nothing but T1 CV plus U plus T2 CV plus U, but T1 T2 are both linear, so you'll have this will be C T1V plus TU, sorry, T1U. Similarly, you'll have C T2V plus T2U, and you can take C together, so you'll have C T1 C of T1 plus T2 of V. Okay, so this is nothing but CT1V plus CT2V, and then this one is T1 plus T2 of U, right? So addition of two linear maps is again linear. Now question is that what happens if you multiply by a constant and then you add this thing, whether this will be linear or not? Okay, so for example, rather if I should say multiply, that is better. Multiply. Suppose you want to multiply by some constant, say k, and we have a linear map T, then is this again a linear? So what we are saying that when you apply this on the vector CV plus U, does this satisfy the similar property of linearity? And the answer is yes, obviously, because this is, you can write down KT of CU plus KT of CV, KT of U, and that is nothing but K CTV plus KTU, and this you can write down as nothing but C times KT of so yes, C times KT of V plus KT of U, right? So see, both the properties are satisfied. This addition is linear, and also you multiply by that thing some constant, so this will be also linear, right? So what does that mean? That means if you collect space of all if you collect space of all, if you collect all the linear maps from V to W, if you define operation like this and scalar multiplication like this, then they will also form a vector space. And this is our new definition. So we define so so let V W be two linear spaces over a field F. So we define something called space of all between the space of all linear maps or linear transformation by this is my symbol LVW. So what is LVW? LVW is collection of all F, all T, whatever, from B to W, and such that F is linear. Okay. And then this observation, previous observation says that then this LVW is also a linear space with respect to which operation? The operation is what? So this f1 plus f2 of x, that will be nothing but f1x plus f2 of x. So this is the addition, and scalar multiplication is what? C times f of x will be C of f of x. If you take f of x, then multiply by C. Okay. With respect to these two operations, LVW will be a linear space. Okay. And in particular, when V equal to W, then we write down LVB. So LV. So what is LV? LV is nothing but LVB. So both domain and codomain are same. In that case, we write down LV only. Okay, so we don't write down twice V. Only one V is enough. This is the symbol. Okay. So now the natural question is that suppose we have two vector spaces. Suppose you are inside LVW, and then if you know the addition of two linear maps, second linear map, then what happened to their matrix representation? So what happened? So this is another question you can ask, that what will be the matrix representation of element of the LVW. Okay, so how do you represent? Okay, and then obviously you can have the answer to this theorem. So that tells you that suppose you have two maps, say T1 and T2, from say, or rather I don't write down that, I write down LVW. So this is my symbol now, LVW. So that means linear map from V to W over the same field f. Okay, and now I am also obviously assuming a V and W are fine dimension, otherwise it's not possible. And suppose with respect to so you choose some basis, BV and BW. Okay, so this is basis of V and W respectively. So their basis of V and W respectively. What was my question? That then this addition will be what, like, and the question then answer is that T1 at T2, we add to the linear maps. If you want to find out what is this will be a linear, and if you want to find what is that basis, a metric representation of this with respect to these bases VV and VW, and the answer is this is actually nothing but addition of the individual one. So what does that mean? That we find out T1, that is you already know. Okay, and then add with the metric representation of T2, that is also you already know, and done. Then the addition will be this addition of matrices. Okay, and the proof is similar because okay, so and obviously that is true, similar thing is true for the multiplication. For example, you multiply by k with say T1 with respect to the same basis BV and BW, and this is nothing but you first whatever is known, write down that matrix, okay, with respect to that, and then multiply that whole matrix by the constant k. So that means it is an entry-wise multiplication. Okay, and that is true for every k. So this is true for all k belongs to the field F, where both the linear spaces over this field. Okay, now the proofs are also simple. So how do you prove? Proof of one. So you have this basis vector v1 v2 v1 v2 vn, and bw is w1 w2 wm. Okay, then what do you know? You know that T1, so let me write down this symbol T1 of Vj, that is summation Aij Wi I equal to 1 to m. Okay, and T2 of Vj, so let me write down by this symbol some another constant, so Bij and omega I w whatever I equal to 1 to m. Okay, now with the help of these two things, what do you know? So if when you add those things, two vectors T1 two maps T1 T2, and when you evaluate at the point Vj, to find out the metric representation, you need to add at V that point, right? So what will happen when you are going to add those things? So this will be actually addition of these two identity, right? And that will be nothing but Aij plus Bij, then I equal to 1 to m, right? And this is exactly that tells you that, so this is the jth, so this is jth column, right? So for every j, the jth column is of this form. And what does that mean? That means that when you the matrix representation of that. So this is the addition of two things, right? Okay, so I'm not writing anything more. So this is obvious now from here that I've written. And similar thing is true for k times of t1 also. K times of t1, right? So for k times of t1, so what you do? So you multiply k vj, and that is nothing but summation k eij omega I equal to 1 to m. So these two equation you can easily find out the answer. Okay. So now obviously you can evaluate this with examples like you can check. Maybe I can ask you, give you some example. Okay, so let me find out. You will have more understanding. So example. So maybe my V is some so P3 R and W is P2 R. Okay. What was that one map? So we define the linear, I think T1 of that the derivative map, right? Px, P dash x, right? Now obviously this is one map, so you can have different linear maps also. So T2 derivative of Px. So this is let me define by 2 maybe double dash x plus P dash. Okay. Yeah, so you can check it is also linear map. Okay. And now what are the individual matrices? So I remember the matrix. So maybe A1 is the matrices for T1. With respect to standard order basis, I'm not writing again. Okay. So what was the basis? So B1 was basis of V, which is 1 x squared x cube, and V2 was the basis of V2R, which is 1 x squared. Okay. Now with respect to these two bases, I think we have calculated already one matrix. So let me see. Yeah, 0, 0, okay. So 1, 2, 3. Other thing is 0. Okay. So this is maybe A1. Let me write down A1. That was 0, 0, 0, 1, 0, 0, 0, 2, 0, 0, 0, 3. Okay. Now let us calculate for T2. So for T2, what happened? Let me write down T2. So what does T2 do? T2 sends ones to where? See, T2 is 2 P double dash plus P dash x, right? Now 1 will go to 0, 0. So 1 will go to 0. Which is nothing but 0 times 1 plus 0 times x plus 0 times x square, right? What does do T2 with the monomial x? So that goes to to double dash. So again it is 0 and this is 1, right? So this is go to 1. So this is 1 times 0 plus, sorry, 1 times 1, not 0. 1 times 1, 0 times x, 0 times x square, right? What happened with x square? Now see x square, here double derivative is 1, 0, right? So if you multiply x square first one times, they will have 2x. Again, if you do derivative, then they will give 2. 2 into 2, 4 then. So the first one is 4 plus 2x, and that is nothing but 4 times 1 plus 2 times x plus 0 times x square, right? Similarly, t2 of x cube, what does it do? So if first one derivative, then it will have 3x square. Again, if you take derivative, then it will be 6x, right? Yes, 6x. And there was a 2, so 12x. And the second one is 3x square. So it will be 0 times 1 plus 12 times x plus 3 times x square, right? So what is the matrix? So here I choose A1. Now let me write down this A2. This is matrix with respect to matrix of T2 with respect to that standard order basis. So I am not writing again the basis here, but this is you can understand, right? And this will be nothing but the first one is 0, 0, 0. Second column is 1, 0, 0. Third column is 4, 2, 0. And fourth column is 0, 12, 3. Okay. Now we check. Okay. Now we'll check that if we add those two vectors, two matrices, that will be matrix for T1 plus T2. But let me find out separately. So what will be T1 plus T2 of the polynomial? How it does? So this will be, if we add those two things, you can understand that 2p dash x plus 2, right? So you have 2p dash x plus 2p double dash x, right? And here if you want to calculate it, so you can easily calculate. Okay, so maybe, so I am giving you a homework. Now you calculate that this T1 plus T2, this will be the same basis. This will be nothing but A1 plus A2. Okay, you just calculate it. And what is A1 plus A2? So A1 is 0, 0, 0, 1, 0, 0, 0, 2, 0, and 0, 0, 3. What was A2? A2 was 0, 0, 0, 1, 0, 0, and then 4, 2, 0, 0, 12, 3, right? 4, 2, 0, 0, 3, 4, 2, 0, 0, 12, 3. Okay, so now if we add those two vectors, then whatever, the first column will be same, second will be 2, 0, 0, third will be 4, 2 plus 4, 4, 0, fourth will be 0, 12, and 6. So this will be the matrix representation of T1 plus T2, that you can easily find out from here also. Now check it. Okay. So maybe I will stop here. So this is a new idea, and now I need to do practice with many examples. Okay, so I will stop here for today's lecture.